Additive manufacturing, more commonly referred to as 3D printing, has been a hot topic in today's society. In our modern engineering world, this technology has started to become a central component for rapid prototyping, customization of parts, and overall creation of new ways to produce solutions to the many problems we have in our world. However, there is so much more potential with the current use of 3D printing methods to produce better outcomes and unique solutions, especially within the medical device industry. Enter the Bioabsorbable Cleft Scaffold project. Our team's focus is to design a 3D printed bone scaffold for the alveolar cleft capable of withstanding the mechanical forces associated with bone growth and containing porosity for cell growth promotion. The goal is to provide structure to the void created by the cleft palate while containing porosity for bone cells to grow into the scaffold and slowly replace the structure over time as the scaffold degrades. For babies born with cleft palate, this new method could save them from needing numerous procedures and hospital visits throughout their lifetime, as well as provide a custom fit to their specific defect size and shape, both saving them and the hospital's time and money. The Center for Disease Control reported that there are around 2,700 cases of cleft palate in the United States each year. While this specific market may seem small, we wanted to focus our effort here as a team because we believe if we can tackle this cleft bone scaffold solution, we can expand into the bone graft market as a whole. That market has over $2.5 billion in sales each year, with about 2.2 million bone graft procedures worldwide.
In order for the scaffold to be a practical solution, it has to be designed to withstand a 500 Newton force to ensure that it would not deform due to suckling or biting done repeatedly by the baby. It also has to contain 300 to 800 micron pores in all three dimensions to ensure that the scaffold can be populated with cells and those cells can receive nutrient flow when the scaffold is implanted in the body. The design we have come up with works through CT scanning the head of a patient with a cleft palate deformity. Then that CT is ran through a few programs to help isolate the bone and create a scaffold for the void by mirroring the opposite non-defective side of the skull. From there, the model is brought into SolidWorks and a 3D pattern of pores are designed into the scaffold. Then the scaffold is ready to be sent off to print.
The team has done extensive research on various bioabsorbable materials for use in this scaffold. We ran simulations in SolidWorks with 4 potential material compositions on 2 scaffold pore sizes of 500 and 800 microns to verify that these materials will meet the design requirements. The resulting displacement values were found based on a compression force of 500 newtons. These simulations confirmed that polycaprolactone mixed with tricalcium phosphate will provide the best scaffolding approach as this material mixture experienced the smallest displacement. We believe this is the best solution because it can replace the need for multiple surgeries by allowing the patient's own bone to slowly populate the scaffold space. It also is customizable for each patient, allowing specific solutions for varying cleft sizes and shapes. These porous scaffolds can be seeded with cells before implantation to help promote the development and growth of actual bone cells into the scaffold space. There is work left to do in terms of finding a way to successfully print these scaffold designs. Once this is achieved and scaffolds are printed, the results of the simulations can be verified. Test equipment such as a microscope and load frame can be used to confirm pore size and mechanical properties. Furthermore, the scaffold degradation rate will need to be compared to and tested against the bone ingrowth rate to ensure that the palate will be supported throughout the entirety of the healing and growth process. We believe that this project will continue to push the boundaries of what 3D printers and mechanical devices can do to improve the world around us.